Hello, good evening, everybody. Wishing everyone a happy International Women's Day. Welcome to the EdTech Society's Masterclass series. I hope you all are enjoying this series that we have curated for you. Last Masterclass was by Dr. Florence on cybersecurity education. If you missed watching it, you can access it from the EdTech Society's YouTube channel. Today, we have Dr. Rumana Pathan for her masterclass on Learning Analytics in Technology Enhanced Learning Environment, Automated Detection of Metacognitive Processes. Welcome, Dr. Rumana.
Thank you so
Dr.
much.
Rumana Pathan is an educational data analytics researcher. She focuses on making learning visible and measurable through data driven approaches, helping educators enhance student learning experiences. Her research combines educational technology with data science to analyze learning processes across web based learning environments, mobile applications, and immersive technologies like augmented reality and virtual reality. She has a bachelor's and master's in computer engineering and a PhD from Center for Educational Technology, IIT Bombay. Over to you, Rumana. We all are waiting to hear from you about your talk.
Thank you very much, Lakshmi. Let me share my screen.
Sure.
Is my screen visible?
Yeah, it is now visible, Rumana. Over to you.
Okay. Good evening, everyone. Welcome to the masterclass on learning analytics in TELE. Specifically, I'll be talking about automated detection of metacognitive processes. But before I start, let me start with a quote that is very famous in our learning analytics circle at Tech IIT Bombay. Data, data, data. I can't make bricks without clay. Any guesses where you have heard this famous line from? Many of you must have guessed it right. It's from the famous novel Sherlock Holmes by Sir Arthur Conan Doyle. So it's a fact that we are awash in data, and data is nothing but a collection of facts. It could be numbers, pictures, videos, texts, measurements, observations, the product reviews you write, the fitness tracker, the steps you count. Everything is data. Now, what is analytics? Analytics is nothing but how you put data through use. For example, we use this data, we collect this data, we transform this data, and we organize to come up with useful conclusions, important predictions, and make informed decisions. Now that we know what data analytics is, what is learning analytics? Learning analytics is nothing but data analytics to enhance education. The Society of Learning Analytics and Research, the SOLAR community, defines LA as the measurement, collection, analysis, and reporting of data about learners and their contexts for purposes of understanding and optimizing learning and the environments in which it occurs. There are several key uses of learning analytics, which includes providing personalized and timely feedback to students regarding their learning. It is also used to foster key skills such as collaboration, communication, creativity, etc. LA is also being used to develop student awareness by supporting self reflection. And most of the insights that are data driven insights are used to validate and improve teaching methods. So, this is LA in nutshell for you. Now, in this talk, we'll be talking about this particular key use, but we'll also be mostly talking about how do we identify these key learning processes so that we can make a provision for personalized and timely feedback. So, having this background, let us now delve into learning analytics in TELE. So, TELE is nothing but a technology enhanced learning environment. So imagine you are a novice learner and you are solving a complex engineering problem in a TELE. And in order to solve this problem effectively, you have to undertake a number of things. Like, for example, you have to activate your prior knowledge about the problem. You have to set meaningful sub goals to be able to complete this problem on time. You have to monitor your emerging understanding, use strategies to facilitate your knowledge acquisition, and also follow advice from scaffolds and prompts. This sounds a lot, right? All these things that the learner is expected to do is called as cognitive and metacognitive processes, and these processes play a huge and critical role in problem solving. Now, although these processes are very desirable, learners find it very difficult to execute. So, from literature, we know that learners do not monitor and regulate often, whereas experts regulate effectively. Hence, there is a need to support these novice learners to identify these processes and to detect these processes. So, now when the learner is solving a problem and undergoing or displaying this metacognitive processes, this mostly happens in a very tacit manner, which is not visible to us. What is visible to us is when the learner reports himself. Like, for example, the learner says, I should start from this goal. If the learner says this, we know that the learner is trying to set a meaningful sub goal. So we have this invisible plane where the learner is undergoing these metacognitive processes by himself, and there is an interpretable plane where we can interpret what the learner is doing by the means of what the learner is reporting to us. In addition to this, there is one more plane that is called the observable plane, where we are able to see what the learner is doing via computer generated learner action. So you can see that we're able to see the learner is doing particular action at this particular time and on this particular page. So we have this observable plane now. Our goal in this talk is to be able to identify these metacognitive processes using observable plane, and to be able to assess our solution with the interpretable plane here. So, for simplicity, I've structured my talk in three parts. So, imagine this as if answering these three important questions. What are the metacognitive processes that we can identify in a TELE? How do we identify them automatically? And towards the end, we'll also see why do we have to identify these processes? Why do we have to study the role of metacognition on learning? So, in order to understand first the what part of this talk, let's first understand metacognition. The term metacognition was coined by Flavel in 1976, and it means nothing but knowledge about one's own cognitive processes, their outcomes, and anything related to it. So, metacognition is regulation of cognition. That is how learners execute these various cognitive and metacognitive processes, such as planning, monitoring, control, coming up with strategies, and evaluation. So, there are several theoretical models that outline these metacognitive processes. Zimmerman, Pentrich, Winnie, and Hadwin, these are the most empirically tested theoretical models that are there in the literature. And this also form a very seminal work in self-regulated learning research. Let me show you one such model. So this is Pentrich's model of SRL. So you can see that Pentrich has divided phases and area for regulation as a heuristic to organize thinking and research. You can see that Pentrich has categorized phases of learning as forethought and planning, monitoring, control, and reaction and reflection across various areas for regulation, such as regulation of cognition, motivation, affect, behavior, context. In this particular talk, we'll be only focusing on the extent of regulation of cognition. That is the phases and the metacognitive processes that fall under metacognition. Yeah. Now, what are the different ways of identifying metacognition? Um, in literature review, we came across three major ways of measuring these metacognitive processes. The first one being self-report lens. So this is a famous questionnaire, MSLQ questionnaire, widely used. and wherein learners self-report their knowledge of cognition, what they think about their planning, monitoring, control, and evaluation. One, although these questionnaires are very easy to gather and gives us a lot of insight about what the learner perceives about his metacognition, there are certain disadvantages. So this metacognition, in this particular way of measuring, we lose out on the temporal aspect. We don't know what particular metacognitive process is occurring at what particular stage. So the time information that comes with it is lost. And in addition to this, from some previous research, we know that novices are poor calibrators of their learning. So the data that is being generated, that is being collected, may not be valid in some cases. And the next one is think aloud protocol. So when you to measure metacognition, there are two major think aloud protocols that are commonly used. One is the concurrent think aloud protocol, and the other one is retrospective think aloud protocol. Concurrent think aloud protocol is nothing but, so when the learner is solving the problem, we ask the learner to concurrently verbalize uh, what the learner is thinking. So this is basically thinking aloud during interaction with the learning environment. Here there is minimum interaction with the researcher except for very simple prompts like keep talking. On the other hand, the retrospective think aloud method allows a learner to solve the problem completely, and the interaction is recorded using screen recording and is used as a cue to ask learners to verbally report after the task has ended. So this is more like a open-ended interview protocol that the learner is going through. So in the first case, the think aloud, the CTA protocol, this enables us to follow the thought process of learner as they occur without having the time to rationalize their thoughts. But the disadvantage of having this particular CTA is that they have to constantly think aloud along with solving the problem, which may cause some hindrances. In On the other hand, retrospective think aloud yields elaborate and explanatory data about why the learner took certain decision. But there are disadvantages such as the retrieval process may not produce all the information, and that there is a possibility that the learner is creating answers on the spot and giving us rationals which may not be even true which may not be even be true. Now let's look at identifying metacognition using computer-generated traces. So there are several research studies that use this method to identify metacognition. You can see a number of research groups that have published papers to identify metacognitive processes. So the most common method is using data for human distillation of data for human judgment, followed by relationship mining using SPM and process mining, followed by clustering to understand learner behavior in SRL, and prediction and classification. So the gap that we found is that although there are many methods to automatically detect these metacognitive processes, we found very few studies who triangulated this the information that we found from computer generated traces with methods that are close to ground truth. When we say ground truth, we mean information like concurrent think aloud data. Let's go back to identifying metacognition using think aloud protocols. So you can see that a learner here is verbalizing his thoughts. The learner is saying, I do not understand this. Does it mean I can create a causal map of my own? So how do we map this particular verbalization of the learner to a metacognitive process? In order to correctly infer what a learner is saying, we came up with a list of indicators. And indicators are observable pointers that can be representative or suggestive that a particular regulatory process is taking place. So, for example, for the metacognitive process judgment of learning, we looked at the literature and we consolidated a few indicators that indicates that the learner is displaying JOL. So you can see that here the learner, the indicator states, uh, learner becomes aware that he does not understand something they just read or heard. So this indicator exactly maps with the verbalization the learner is saying, I do not understand this. That doesn't mean I can create a causal map of my own. So with this, we are able to say that the learner is displaying or undergoing judgment of learning, which is a monitoring phase. Let's look at some more example. These are the metacognitive processes. These are the indicators that we found from literature. And these are the corresponding learner verbalization we think map to this. So you can see that here the learner is saying, I learned the concept of friction. When a body is moving at a normal speed, the surface it's moving on, whether it's a floor, track, or anything else, will oppose its motion. So the learner here is activating his prior knowledge by actively searching their memory for relevant prior knowledge. This indicator is mapped with activation of relevant prior content knowledge. You can also see that this example wherein this learner is saying that I don't remember, but I could recollect some part of the formula. So this maps with the indicator that the learner is aware of reading something in the past related to this and having some understanding of it, but is not being able to recall it on demand. This maps with the metacognitive process feeling of knowing, which is a monitoring phase. So similarly, we have examples for model building, which is a control strategy, wherein you can see that the learner is talking about using a causal map to discuss the maximum and minimum changes. And our indicator also suggests that using a causal map is an indication of displaying model building sub-goal, model building metacognitive process. Yeah. So, in a similar manner, we came up with a huge list of indicators. So, you can see this research paper wherein we have come up with 48 indicators that are aligned to 17 different metacognitive processes, such as target goal setting, activation of prior knowledge, cognitive tasks, etc., which are further mapped to 4 phases, that is, planning and activation, control, regulation, reaction and reflection, and monitoring. So you can find the indicators and here in this paper. So this is what the entire indicator list looks like. So if you have verbalizations by learners, you can use this table to identify whether the learner is displaying planning, monitoring, etc. Now, let's come to the part how to identify these metacognitive processes automatically. Now, before we proceed, I want you to become familiar with the terminology that I'll be using here. So, when I say raw log traces, I mean traces such as mouse click of learners. When the learner is interacting, the learner uses the mouse as well as clicks and writes and types. So, all these are tracked using the log data along with the timestamp, the user ID, and the session ID. So this is what raw log data looks like, more or less. Now, this raw log data was huge. Like we had around 500 to 700 different clicks and mouse clicks and buttons that were not making much sense. So what we did was we converted this raw log data into learner actions that were meaningful to us. Like for example, here you can see that these are categories of learner actions that signify what the learner is currently doing. So when we say tutorial, it means that the learner is reading or rereading introduction or the general instructions that were posted, the information about the sub goals, or is watching the introduction video. So when a learner is in tutorial, the learner could be doing one of these things. Now that we have these meaningful actions, we created a set of rules to identify metacognitive processes. So these rules are nothing but sequence of actions and time information. So you can see that tutorial followed by long. So what we mean by long is if the learner is spending more than 10 seconds. So we identified 10 seconds because we saw that if a learner is spending more than 10 seconds in our particular learning environment, the action was a bit meaningful. So we termed it as long. So here you can see that the learner is spending a long time going through the tutorial, followed by read problem statement. And this we clubbed in planning and activation. So I'll discuss a few more examples to help you understand how we came up with this set of rules to identify these processes. So you can see here, the learner is creating a hypothesis for more than 10 seconds, followed by reading a problem statement. So here, the learner is navigating to a problem statement during creation of hypothesis. So a learner might be doing this to build a better problem representation. This is exactly what our indicator tells us. Learner constructs a better problem representation. So what we did was we scanned through this list of indicators and we identified sequence of actions that would tell us that this particular indicator is taking place. Let me give you one more example. So you can see that here the learner is calculating a value for a long time, followed by evaluating the value. So this is nothing but cognitive judgment, where the learner is evaluating his answer or his performance. Now, how do we ascertain that the learners are indeed undergoing these metacognitive processes? So what we did was we collected concurrent think aloud data and we coded it using the coding mechanism that I discussed earlier. And we also put the log data, the actions, that is create hypothesis, etc., across a synchronized timeline. So we collected both this both this data together and synchronized it across a common synchronized timeline. So you can see that from the think aloud data, we know that the learner is setting a specific goal for learning, which means that the learner is planning and activating its prior knowledge. On the other hand, when we looked at log data, we saw that the learner is creating a hypothesis followed by reading problem statement. So, as per our information, this is also planning and activation. So, you can see that the information that we got from Think Aloud data and information from log data is matching at certain points, but is also mismatching in certain areas. So, based on this triangulation technique, we calculated a match rate, wherein we calculated by calculating the total number of matches divided by matches plus the mismatches. And we saw that using our rules, we could identify 30. We had a match rate of 39%. That means only 39% of the time we were able to correctly identify a metacognitive process using log data. This is using the rule based method. Now, so here we in this particular method, we were only using sequence of actions. So we wanted to know what if, apart from sequence of actions, there are combinations of actions that are useful in identifying this metacognitive process. Now, in order to implement that, we used a machine learning technique. So in this machine learning, we extracted features along three dimensions. So we looked at information such as learner actions, the time spent in these actions, and the sequence of actions in which it occurred. For example, if we want to um, identify what the learner is displaying at evaluate model, we would look at the previous actions before this evaluate model. So in our case, we looked at three unique actions. So here it is create hypothesis, read problem statement, and tutorial. We looked at only three actions because from our sequential pattern mining, we saw only three sequence coming up. We did not find four action long sequences commonly emerging. So That is the reason we kept it at 3. In addition to the three recent learner actions, we also recorded the time spent in each action, and also the sequence. The sequence as a tutorial occurred first, followed by read problem statement, and then create hypothesis. So this is how we created features along the three dimensions. Now, since there are multiple metacognitive processes and phases, we had to handle this multi-class classification and also manage the imbalance in the data. So we used a one versus all solution where we created different classifiers for phases and tested them. And since we had an imbalanced data, we upsampled the minority class instances using a technique called as MOTE, and we employed machine learning models that are proven effective for small data sets. What we did was we trained 70% of the upsample data, and we tested our models on the 30% of the data that was not sampled. And we calculated the performance using classification accuracy and the F score. So, our machine learning model, in this case, a random forest model, which was the best performing model, accurately classified around 77% of the phases. So, the classification accuracy was 0.77, which is way better than the rule based model that we discussed before this. But the problem here was, since this machine learning model classified automatically, it was difficult to explain how the phases are being detected, what were the sequence of or combination of actions that led to detection of this particular metacognitive process. So, in comparison to this, wherein our rule based model accurately identifies 39% of phases, in addition to this, our model was also able to provide information on occurrence of phases that is instrumental in providing informed feedback. So, in identifying processes automatically, we have explored two methods: one machine learning and one rule based. And although the accuracy is higher in the ML part of this exploration, we also feel that the rule based model is very instrumental in providing us information on the phases, occurrence of phases. Now let's look at the why part of it. Why do we identify metacognitive processes? What is the use of it? So, from our research studies, we found, and several existing research studies, we know that there is a significant positive relationship between metacognitive processes undertaken by learners and their performance in the learning task. That is, metacognitive skills such as planning, monitoring, reflection are linked to higher academic performance regardless of intelligence or motivation. In our research studies, we also found that although learners display similar interaction in the TELE, the metacognitive processes undertaken during the event determine the performance. So, this gives us a cue as to by identifying metacognitive behaviors, it helps us clarify why some learners succeed while others struggle, even with similar prior knowledge. And it also helps us recognizing specific metacognitive gaps, so that researchers can design strategies to improve learning, especially for low performing learners. So let me give you an example of from my research study. So we wanted to explore the role of metacognition in learning, and we came across this this sequence of action by high, medium, and low scoring learners. So you can see that all three categories of learners: evaluate, estimate, followed by feedback, in all three categories. But what is different here is the metacognitive phases that they are displaying at this point. So you can see that the high scoring learners, in addition to this interaction, are displaying very high reaction and reflection during during the interaction. On the other hand, medium scoring learners are displaying control and followed by planning and activation, whereas the low scoring learners are not displaying any phase at all during feedback. So it shows us that although these learners display similar interaction, the metacognitive processes that are undertaken during this event determines their performance in the learning task. It also creates a gap for us to intervene and help the low scoring learners. For example, at this point, if it is detected that a learner is not showing any phase, metacognitive phase during feedback, a possible metacognitive prompt can be given, such as evaluating why you went wrong and planning during feedback helped your friends arrive to the correct answer. So, this very gently nudges the learner to also think about planning and evaluating at this feedback stage. Let me give you one more example. So this is process model that we have created of high scoring learners. So this process model is ordered temporally based on timestamps, and the arcs that are joining the two events indicates the reliability of the causal relationship. We have calculated this using a frequency based metric. For example, this particular relationship occurred 33 out of 50 times, so it is 0.78. Now what we did was, in addition to this process model, we overlaid the process model with information of predominant metacognitive phases that were undertaken by learners during an event. So you can see these oval shaped overlays that are color coded as per metacognitive phases. And one thing to note here is that the shape and size of the overlay do not indicate the intensity of metacognitive phase. So let me explain you one such result here. So you can see that high scoring learners showed a pattern of creating causal map while interacting with simulators significantly, and they did this while displaying or undertaking control and regulation process. Similarly, high scoring learners, when they saw that their evaluation of their model is incorrect, they answered the metacognitive prompt. This they displayed while showing monitoring ability. So this is an important finding for us, because it shows a very desirable pattern that a high scoring learner is showing at this point. So using such sequential pattern mining methods and process mining methods, we came up with key problem solving and metacognitive characteristics of different kind of learners. So for example, high scoring learners, so these are some nitty gritties of what high scoring learners do. So overall, we just have to know that high scoring learners undertake a lot of different kind of metacognitive phases frequently during different stages of problem solving. On the other hand, what a medium scoring learner does is it displays a lot of use of control and regulation and planning and reflection and monitoring in some part of problem solving, but not all the time. And you can also see there's a stark difference in the low scoring learners. Low scoring learners predominantly only undertake control and regulation, and also they do not display any phase during important events like feedback. So you can see a visual difference between high, medium, and low scoring learners and the kind of metacognitive processes that they use during different problem solving stages. Why this is important? So this is important because it forms a metacognitive profile of learner. By detecting several productive and unproductive learner patterns, it enables us to come up with adaptive scaffolds to provide timely and personalized feedback to, say, low scoring learners, and also maybe to challenge high scoring learners. Okay, so let me summarize what we have learned so far in this talk. So we saw that to identify metacognitive processes, there are several SRL frameworks that outline metacognitive processes, and this can be identified using both think aloud and trace data. How to identify the metacognitive processes automatically? In this talk, we explored two ways. One was the rule based method, and the other was machine learning based model. And as to why, we saw that the metacognitive processes are closely linked to better learning performance, explain differences between learners, and also guide personalized support for improvement. Okay. This was about identifying metacognitive processes in a TELE. Now, what else can we achieve using learning analytics in TELE? So I have come up with a few examples that I have experienced in my short research profile. So let me show you this uh, work wherein we analyzed log data from a mobile application. So this is an application called as Hello English, which is a very popular English language learning application for native learners. So it allows around, I think, 23 languages learners to learn English in their mother tongue. And here the learners interact with this application. They read newspaper, they collect points, they play games, they solve challenges. So it's a very interactive application. Although it has all the good elements of a good mobile application, we saw that many of the learners who were interacting were dropping off after a certain point. So the challenge in front of us was, can we use learning analytics to identify or to early predict the uninstall behavior of learner? And yes, we were able to do so. So we looked at log data, the interaction data of around 700 learners, and we saw that we could early predict learners uninstall behavior as early as day 4. So prediction of churning behavior we were able to do with a high recall value from day 4 onwards. And this information was helpful to develop interventions to persist learners from dropping off. So we were able to recognize the interaction that would lead to churning, and on identifying, we could give them interventions to persist the learners to stay back on the app so that they can learn more. Yeah, so this is about a mobile based application. Now, let me show you a virtual reality based learning environment. So, this work of ours involved learning about human circulatory system in a VR environment. So, you can see that this is the inside of a heart of a human being. And the learner could wear VR headset and could navigate inside the human circulatory system. So you can see this is the gaze pointer. We could identify where the learner is looking at using this gaze pointer. There are various 3D objects. You can see this is a ventricle, left atrium. This is the textual information associated with the 3D object. And there are navigation cues. So after learning about, say, left atrium, the learner could navigate to some other learning scene. So this was the navigation cue. The learners could also switch scenes, and there was an audio enable and disable button. So what we did was we recorded this learner interaction, and we logged their interaction. Like, for example, along with the student identifier, we logged their action, whether the learner is looking at a particular VR scene for a long time, or is reading, or is following a navigation cue. If it is following a navigation cue, from where it is following it, is it following from right atrium to left ventricle? So on. We collected the actions and the context and the time. So having such kind of log data in virtual reality environment enabled us to find some interesting results. Like, for example, there was a very interesting finding where we saw that learners were reading more in the virtual environment than looking at the 3D images in VR. which was surprising to us because we were expecting learners to spend more time in absorbing the 3D images that were so realistic. We also saw that high scoring learners did not follow navigation cues after a certain point. So once they have visited the scene, when they were revisiting, they were not following the navigation cue, which was suggesting that the learner is probably exploring on their own. And maybe that was helping them score high on the test that followed. We also understood how different VR features are supporting learning, and this overall helps us design effective VR learning environment, because although VR has reached a very high potential in gaming, for education there are a lot of questions revolving around its efficacy and how do we best support learning using the features of VR. This is an extension of the work that I was talking about here. So in this previous case, we were only able to look at the gaze pointer, but here you can see my colleague uh, interacting with Meta's Oculus. So this is work of Anthony Prakash, his PhD work. So you can see that he is interacting with some gears as well, with some triggers. So what Anthony is doing here is in the virtual reality environment, he is learning electromagnetism. So he's moving a magnet through a coil, and he's looking at the EMF force that is being generated. So apart from the gaze, that his entire body is being engaged in the VR learning environment. Now there is very little information about how do this behavioral data support in learning. So this work involved in uh, logging all this information in VR in computer. So you can see that if the candidate presses a right trigger, or the trigger is held, that is being captured along with the timestamp and the object that the learner was has interacted with, and whether the learner has clicked any information. So all this information is being logged in an environment that is far beyond just involving your eyesight, but also involving your body. So with this kind of interaction, we were able to identify that learning outcomes vary among participants due to differences in the interaction behavior. And the high performers exhibited a high number of relevant interactive actions and spent more time in engaging in those actions as compared to low performers. So the next environment that we have worked with is augmented reality. So you can see this is an augmented reality application where the learner is scanning a card and is able to see the 3D model and interact and modify the 3D model with his finger gestures. There's also a web-based application which is displaying an activity that the learner is doing. So we developed this application called as GeoSolver to help learners do mental rotation, or to be able to train them to do mental rotation. So this is an important ability to retain an object and accurately rotate it in space. This helps us understand geometry concepts like visualization of 3D solids from 2D, etc. Here what we did was we captured the interaction path of the learner using logs, such as when the learner was looking at the question, when the learner was observing the 3D model, when the learner was looking at the feedback, etc. So by logging such interaction, we were able to see that we were able to analyze that high scoring learners completed rotation tasks as per requirement, whereas low scoring learners performed only partial rotation of the objects. And this is probably why high scoring learners were getting correct answers on their rotation. And we also saw that high scoring learners used the AR application during feedback stage despite no instruction to use the application. Yeah, so my talk has come to an end. These are some possible future extensions that are possible. We can characterize these learning processes, specifically metacognitive processes, using additional modalities. So we've only looked at log data. We can also use at modalities like facial expressions, eye gaze, movements, to capture data occurring in smaller time frame of time. And there's a lot of work that needs to be done, using automatic models to detect metacognitive processes, so that we can give personalized and adaptive feedback to learners when it's needed. These are some final reflections from my work. So we saw that I saw that some metacognitive processes need an advanced technique, and but need an advanced technique. Although we are able to identify only certain, say 39% of the metacognitive processes currently correctly, even such partial detection of metacognitive activity helps us or enables adaptive scaffolding, and it clarifies the role of metacognition in SRL. And personally, this has helped me a lot understand the learning processes that are involved in diverse educational journeys. So for me, it was involving myself in understanding how learners uh, display metacognition has been very insightful. And uh, thank you for being on this journey with me too, and listening to my thoughts.
Thanks, Romana. Um, there is a question which I'm going to be reading it to you, and you can also see on the screen, by Sunny Satpati. Based on the findings from the paper, would you consider using a machine learning model to analyze data at scale and then go in with a rule based model for a deeper understanding?
Um, Thanks, Sunny, for the question. That's a very good question. So you can see, so the machine learning model, the data that we fed to the machine learning model was very contextual. It was very local to the research study that we conducted, local to the the environment that we have taken. So if I have to identify metacognitive processes on a large scale in the same tele as I've already my machine learning is trained on, I will definitely use a machine learning model to identify metacognitive processes, because here my concern is to be able to only identify. But if my motive was to understand why this metacognitive process is taking place, I would go for a more theoretically based model, because it would give me information on why this particular process is coming up. So you're absolutely right. I would go on and use an ML model and find out places where I have more interest, or places of interest, and would use a theoretical model to go deeper and understand why it's occurring in that manner.
Yeah, thanks, Romana. There's one more question coming up by Marina. Can affect also be measured as a part of the metacognitive experience?
Yes. There are different. So when you say effect, it is a part. So let me rephrase it. Okay. So when we say a learner is doing self-regulated learning, it's not just regulation of cognition, that is metacognition. It is also his regulation of affect, motivation, and the context. So yes, affect is a part of SRL, the self-regulated learning part. And it is also a part, it is also a metacognitive experience. But for heuristic purpose, for organizing our thinking, we are creating a line between the metacognitive regulation and the affect regulation part of it. So the line is a little fuzzy. So there is a difference, but yes, it is also a part of metacognitive experience and the overall self-regulated learning experience as a whole.
Thanks, Romana. Um, Yeah. So we'll just wait for a few minutes before we see some questions. But I have a question. Let's say with all this experience that you have in analyzing metacognition, what are some features that you would recommend for, let's say, edtech entrepreneurs or edtech designers to consider having to enhance metacognition among learners? If you could give us some insights, it'll be really helpful for people who are designers or tech startup people.
So, thank you, Lakshmi, for the question. So, there are a few things that we can consider. Like, for example, in order to monitor, in order to monitor something, we so as learner progresses from, say, one part to another, we can insert specific metacognitive prompts that triggers the learner to monitor at that point. For example, so let me take a moment to answer this and also break my fast. Thank you. So we've seen that when we give specific metacognitive prompts to learners in the beginning of the problem solving stage, where they are asked to plan the next step of action, it really helps them. Although many of the students do not answer the prompt at that moment, it definitely helps some learners to plan what to do next. So specific metacognitive prompts are a must, I feel, at particular stages of problem solving. In addition, we've also seen that when there is a mistake in evaluation, whenever a feedback is provided to learners, we see that most of the learners tend to skip the feedback without paying much attention. So, based on the time that they spend on feedback, we can ask the learners to revisit a particular part of the feedback which would enable them to correctly answer the problems. Like, for example, if we see that the feedback is saying, um, go to this the feedback is saying that the answer is wrong and something else, so we should be able to redirect the learner to better understanding the problem statement itself. So this kind of small adjustments can be made by designers and researchers.
Thanks. That'd be really helpful. There's no more questions coming up, but I have, let's say, one more question. With all these insights, let's say you have integrated learning analytics in a TELE, all these insights are available. How do you envision a teacher using these insights in a classroom, in situ, in a classroom? If you could throw some light about how you have come across teachers using such insights in a classroom.
So I have not come across teachers because the tele that I've used is for an individual problem solve is a problem solving environment where learners are solving a problem on their own, and all the material that is required to help them solve the problem is available on the tele. So I've particularly not explored the aspect, but I can imagine teachers using information such as, for example, a pie chart of the metacognitive processes that the learner used can be shown to a teacher on the dashboard of the teacher, so that the teacher knows that so and so learner has displayed more of planning and monitoring, whereas on the other hand, this learner was not able to show many metacognitive processes, and then the teacher can intervene based on that. So I think a teacher dashboard to show what metacognitive processes during the different stages of problem solving are being used by different learners could be useful to be able to design specific material for that learner.
Yeah, we have no more questions. I think since there are no more questions, I would like to thank the speaker, Dr. Romana. Thank you for accepting the invite and giving us this masterclass on using learning analytics in TELE. And okay, there's a question coming up again.
Okay.
I'm just going to, yeah, okay. There is Sunny who is kind of building up on our conversation about teachers, and she's asking us if would it be helpful for teachers to be trained on the identifier rubric you mentioned earlier.
Yes, of course. I mean, if teachers are able to identify the metacognitive processes, there's no need to even have this tele in place. Teachers, while having conversation during the learner after solving the problem, retrospectively, if the teacher is asking the learner, "What did you do to solve the problem? Tell me the process." If the teacher is familiar with the rubric that I mentioned about, the teacher will be able to identify the different kind of metacognitive processes that the learner has taken, and the effort and the effort that the learner has put in. So it will be helpful for teachers to be trained in this rubric, apart from providing them with a dashboard of the learner interaction.
Yeah, I think
Thanks,
the
Sunny. Yeah.
dashboard. Yeah, thanks, Honey, for building up on this
Yes.
conversation. I think I agree that just yeah, along with providing them the information on a dashboard, it will be helpful for us to kind of identify, um, uh, giving the teacher that as well. Yeah. So with this, I would like to thank Dr. Rumana for accepting our invite and giving us this masterclass. To all the viewers, please stay tuned. We have another masterclass coming up next month. Thank you, Dr. Romana, and enjoy everyone. Have a great evening. Thank you. Bye.
Thank you. Thank you. I had fun. Thank you.